Hi guys, so in this video, we will be covering on design decisions related to a column. A column is a design feature used as a compression element to support the load on top of its surface. Here are some examples of columns used in many engineering applications. A column like this, it have a vertical orientation and it is being subjected to a downward compression load on top of its surface. A long column have a different mechanical behavior compared to a shorter column because when they behave differently, the calculation process are also different. For example, if I apply compression load on the shorter column, then I can calculate the critical load simply using the stress equals to F over A formula. But in the case of longer column, if I apply compression load on top of its surface, before permanent deformation, you see what will happen? It will buckle first. So these mechanics are called buckling. So buckling happens when the length of the column is significantly higher compared to the cross-section of the column. You see, the cross-section of this column is very small compared to the length of the column. So in order to calculate the critical load or the critical stresses for cases of long column, we have to consider the length of the column. So the big question now is, how do you differentiate between a long and short column? How do you know if that particular length will cause buckling? You can do so by using the slenderness ratio. Let's use the symbol lambda to represent the slenderness ratio. Slenderness ratio can be calculated by dividing the effective length to the radius of gyration. Loh, apa pula effective length ni? Apa pula radius of gyration ni? Effective length depends on the type of column joint. It can be calculated by multiplying a constant value K, which is related to the joint type, and multiply it with the actual length of the column, L. The first type of joint is if both end is pinned to a rigid structure. We call it the pin end. Kelakar pula bunyi dia. This type of joint will likely buckle following this trajectory. Almost ideal curve lah. So therefore, the K value for this type of joint is 1. The second type of joint is when both end is simply fixed to the structure. It's not pinned, it's just fixed. So we call it the fixed end. This type of joint will likely buckle following this trajectory. Only half part of it yang buckles. So the K value for this type of joint is reduced to 0.5. The third type of joint is when only one end is fixed to the structure while the other end is free to move. This type of joint will likely buckle following this trajectory. Only half part of it yang buckles. So to get the full curve, the K value becomes 2. The fourth type of joint is when only one end is pinned to the structure while the other end is fixed. This type of joint will likely buckle like this. It have more buckling range lah compared to the fixed end. Therefore, the K value for this type of joint becomes 0.7. So, in order to get the value of the effective length, you have to multiply the actual length of the column to the K value. So, this K value depends on the type of joints for the column, whether it is a pin end ke, fixed end ke, fixed free end ke, fixed pin end ke. Radius of gyration, on the other hand, depends on the cross-section of the column. Let's say we have this rectangular column with the compression force applied on top of the surface. So, if we look at the cross-section of this column from the top view, along the x-axis direction, the radius of gyration would be 0.289 multiplied with h, which is the height of the cross-section which is perpendicular to the x-axis. On the other hand, if we look at the direction of the y-axis, the radius of gyration similarly would still be 0.289, and then you have to multiply it with t, which is the length of the cross-section of the column measured perpendicular to the y-axis. So if you look at the slenderness ratio formula, lambda berkadar songsang or inversely proportional to the radius of gyration. If the R value is high, the lambda will be low, dan sebaliknya jugalah. So looking at the case of a column which looks like the ruler, okay, it have a very thin thickness compared to the width. So the column, if you notice, it will tend to buckle more along the thinner axis, meaning lagi rendah the R value, lagi tinggi the slenderness ratio. Therefore, buckling is higher along the YY direction sebab radius of gyration dia lebih kecil since we refer to the smaller thickness of the ruler. So that is why buckling is more at the YY direction, along the YY punya axis tu, okay? In the slenderness ratio formula, we will take the R with the lower value so that we know what is the maximum buckling magnitude. Back to the main big question. How do we know if the column will buckle or not? How do we really categorize a long or short column? Of course, buckling ability depends on length and also the material of the column. We use a specific measure of column properties called slenderness transition point, CC. The formula have the elastic modulus and yield strength properties in its equation as shown. If the slenderness ratio or the lambda is higher than the slenderness transition point of the column, the CC, then we would classify that column as a long column, which we should consider its buckling mechanics. So if lambda is less than CC, then you would say that the column is short. So we don't have to consider for the buckling mechanics. As an exercise for the attendance for this particular lecture series, okay, why don't you determine the type of the column given? Is it a short or a long column? All of the information are provided in this video slide. Okay, all the best and see you in the next series.